Hi, welcome to the presentation of our work entitled Development of a Family of Nonlinear Controllers. The birth of control engineering began by observing natural phenomena, and from these observations the term feedback was coined. See, for instance, the natural selection and the behavior of populations modified in the presence of predators. In control engineering, feedback means that control mechanisms can be designed through the difference between the actual and the desired output of any system. The essence of control can be stated as the goal of making a system to behave in a certain manner or to do something that we want it to do. Any control problem can be established in terms of the error between a desired output for the task and the actual output of the system. The controller is the input signal that forces the system to fulfill the task that we have defined for it. This is the core of automatic control and the aim of the control theory community. Now, what does it take for the control theory community to accept a new control law proposal? The traditional design of controllers in control theory is handcrafted. The human design process is manual and consists of three main stages. The first one is the problem statement. Here, the definition of the address task and the model of the system are established. In real life, all systems are nonlinear, but in practice, assumptions are made to model the most important dynamics. The second stage is the development and proposal of a control law. The controller defines the input to the system so that it fulfills the task established in the problem statement. This stage is mostly based on previous knowledge of the system and on the designer's experience. The third stage corresponds to the stability analysis of the control system. The stability proof is a must for the control theory community in order to guarantee the solution of the task no matter from where the system departs. The stability analysis is performed on the dynamics that result from including the control law into the system's model, that is, the closed-loop dynamics. If the dynamics are linear, then linear matrix inequalities and/or frequency analysis can be used. If the closed dynamics are nonlinear, then the most accepted criteria is the one established by Alexander Lyapunov, the stability in the sense of Lyapunov. Once the theoretical analysis is complete, the extension to experimental validation closes the cycle. Since control design in the control theory community is handcrafted, it takes a long time to propose a control function that can solve a specific task for a particular system. The most exhausting task is the development of the stability proof. For a human, it can take weeks or even months to develop a single control law using experience and a trial and error discarding process. The stability in the sense of Lyapunov is the most commonly used technique for this analysis, but there is only a guideline about the procedure, and the function must be constructed by hand. The first real PID-type controller was developed by Elmer Sperry in 1911, and its first theoretical analysis was published by Nicholas Minorski in 1922. While there are as many control methodologies as one can imagine, the PID-like controllers are the ones mostly used in the industry. PID controllers are easy to implement and the computational load is small. The PID is the most studied and modified controller in the literature when it comes to control design. Why is it that most solutions offered by the computing community are not well accepted by the control theory community? First of all, this is because of the lack of a stability proof. The main argument refers to the establishment of the space and the conditions where the proposed solution works. The main advantage of the computing community is the arsenal of computational capabilities available. However, due to its numerical nature, it is hard for them to provide an analysis considering the fulfilling of the task no matter the initial conditions or changes in the environment. Another issue is related to the repetitivity of solutions, since the solutions offered by the soft computing community are often probabilistic, especially when dealing with deterministic systems such as those used in physics, mechanics, robotics, and so on. In conclusion, the non-compliance of some conditions makes them hard to be accepted by the control theory community. A step forward in the automatic synthesis of linear controllers was proposed by King, Kosa, and Streeter in 2002. Where linear blocks such as integrators, differentiators, leads, lags, gains, adders, subtractors, and the like are used as ingredients of a genetic programming process. The first paper that we are presenting is Synthetic Analytic Behavior-Based Control Framework, Constraining Velocity in Tracking for Non-Holonomic Wheel Mobile Robots. We aimed for the introduction of a partial controller to fulfill the task while satisfying a restriction on the maximum permitted velocity. We have fed the GP with a model and scenarios that break the velocity bound. It found over 9,000 suitable nonlinear solutions. Interestingly, a lot of them use the hyperbolic sign, either multiplied with other constants or nested with other functions. In addition, many continuous functions with exponential growth and a shape similar to that of the hyperbolic sign were found by the GP. The question is, can they solve the tracking task without the ground controller? The numerical simulations support our idea, but that is not enough. The stability proof is required. It is a global solution. This means that it works for the entire workspace and for all initial conditions. It turns out that there is not just one controller. The solutions found by the GP constitute a family of nonlinear controllers that are globally and asymptotically stable for systems modeled as first-order dynamical systems. The analysis to find a large class of nonlinear controllers introduces our paper entitled Family of Controllers Based on Sector Nonlinear Functions, an application for first-order dynamical systems. The analysis of the nonlinear functions found by the GP allowed us to propose a family of nonlinear controllers that works for systems modeled by first-order dynamical systems. First-order dynamical systems, or FODS, are widely used to model a large variety of systems within robotics, telecommunications, chemistry, biology, sociology, among others. FODS can model the kinematic motion of rigid bodies, agents in networks, and in collaborative systems. They are also used to model walking patterns in humanoid robots and velocity dynamics in DC motors. The main reason why we believe that our work has merits to be considered as the best entry is because it beats the human process of control design. The GP found suitable partial controllers to bound velocity in wheeled mobile robots, and it put us on track to discover a large family of them for a large class of systems modeled by first-order differential equations. We call them S and F controllers. Considering the time it takes to propose a single controller that can solve a specific task for each particular system, the optimized search by the GP allowed the development of a whole family of nonlinear controllers. Our results surpass the human design process in the number of possible controllers. Moreover, we found a procedure to build candidate functions that prove global stability in the sense of Lyapunov, thus fulfilling the control theory requirements. In addition, they share the positive characteristics of the family of PID controllers. For instance, we can tune the decay rate of the nonlinear sector functions with a single parameter. The S and F controllers are easy to implement and the computational load is small since they only depend on the computation of the error and on the tuning of the multiplying constant value. The numerical comparison shows that under bound restrictions in the control input, the nonlinear nature of the S and F controllers contributes to a rapid decrease of the control input, thus reducing their consumption of energy. Another reason for proposing our finding to the Humies is because the controllers discovered by the GP are also solutions for a very different model than the one for which they were designed. The first work uses a solution of the GP as a companion controller, but a particular set of those solutions works as a full controller for a different class of system. Our first paper has been acknowledged as a valid implementation of evolutionary computation using the GP paradigm for the search of fitted nonlinear partial controllers. The discovered solutions provided the basis for the development of a whole family of controllers for a general class of systems. The solutions discovered by the GP have properties that allow them to fulfill all the required mathematical background under the control theory approach for its acceptance by the control theory community. These results were published by the IET Control Theory and Applications Journal, a leading journal devoted to control systems that covers new theoretical results and the applications of new and established control methods. We have already found the stability proof for second-order dynamical systems, which is currently under revision, and our work in progress is addressed towards the extension to systems of higher order. We are currently exploring the extensive area of opportunity that has opened up from our initial work, and we are confident of the possibilities and the impact that this contribution can bring not only to the control theory community but also to the control engineering field. Thank you.